Welcome back, students. Working our way through lesson 4 still. We're all the way up to video 4, part I. Only 2 more to go. Hang in there. The main point of this video is shifting and scaling data. So we'll motivate that with an example here. What I have is a list of homes in Elkton, and we were looking at their assessed value. This is how much their tax is based on for property taxes. I have Zillow Value. That's a website that estimates the value of homes. I have the house's square footage. I have the house's lot size. And at times, we'll take our data, here's our data, and we'll change it. We'll apply a mathematical function to every data value. So I'm not sure why we would do this, but I could add 10 to every assessed value, or I could multiply every assessed value by 1.1, for example. Okay, and so that's what we mean. At times we'll need to change our data. What happens to the summary statistics if we do that? All right, a couple of examples. Say you're taking a sociology course, just had the final exam, and your instructor decides to award a 3-point curve. Every final exam gets 3 points added to it, and the question is, what would happen to the summary statistics? Well, obviously, if everybody gets 3 points added to their final exam, the mean would increase, right? The mean would increase by 3 points. The median would also go up by 3 points. The person that did the best would get 3 points, so the maximum goes up by 3, the minimum goes up by 3. Let's write that down here. So, the mean, median, quartiles, sure, Q1, Q3, minimum, maximum. All of these are measures of position. They're telling you where you're at in the data set. All of these would go up by 3 points. I think it's pretty easy to see that, right? Mean, median, Q1, Q3, min, max, all increase by 3. No problems there, but how about those measures of spread? If you could think of the test scores on a number line, and here's the lowest score, and okay, scores are getting better, here's the best score. If I add 3 points to everybody's score, we just walk them over here. Isn't the standard deviation exactly the same as it was, right? Those measures of spread, when I add something to every data value, there's the same amount of spread as there used to be. So measures of position, things like standard deviation. Oh, what's another measure of position? IQR. And even the range, though we don't use the range all that often, would stay the same. Measures of position all would increase. Measures of spread would all stay the same. And it's important to remember what we're doing. We added something to every data value. Everybody got 3 points added to their score. Okay, second example. I guess we don't have a slide for the second example. Let me erase this and I can just say that one verbally. Not sure what happened to the slide, but part B in your notes, if you're looking in lesson 4, part B says volunteers in a weight loss study have their net weight loss measured in pounds. So we're doing a weight loss study. Everybody's weight loss is measured in pounds. Before publishing the results, researchers convert pounds to kilograms, multiplying every data value by 0.4536. What happens to the summary statistics? I'll head over here to the sideboard just to jot down a few notes, and we'll see what happened to that slide. What are we doing in this one? We are multiplying every data value. If we multiply, I'm converting pounds to kilograms. If we multiply, the mean will get multiplied. So whatever the mean was, it gets multiplied. Whatever the minimum would get multiplied as I convert from pounds to kilograms. Okay? Here, those measures of spread also get multiplied. When we multiply or divide, everything gets affected, and this is actually the easier one, right? If we were doing an add or a subtract, then we have to be careful with those measures of spread. But if we multiply or divide every data value by a constant, what happens is this. Basically every statistic gets multiplied. And it's that same number, it's that 0.4536. So whatever the mean was, we'll multiply the mean by 0.4536, and that will convert the mean into kilograms. Same thing for the minimum, standard deviation, range, IQR, Q3, 73rd percentile. Everything would get multiplied. All right, so back to the main board here. Shifting and scaling. When we shift data values by adding or subtracting a constant to every data value, all measures of position will be changed by that amount. Measures of spread remain unchanged. We've seen this one with the test scores. Measures of spread will remain unchanged. This word shifting here, students, is adding and subtracting, right? Plus and minus. So measures of position will get changed by that amount. Measures of spread remain unchanged. The scaling part. When we scale, a scale is a multiply or a divide. All measures of position, all measures of spread will get multiplied or divided by that constant. So when we scale data by multiplying or dividing by a constant, all measures of position, all measures of spread will be multiplied or divided by that constant. A scale is a multiply or divide. All right. To be sure, we've talked about it, but just to make sure, let's make a quick list of the measures of position, make a quick list of the measures of spread. I'll do the spread first so we can sort of knock those out, and then everything else goes up to position. But as we know, SD, standard deviation, is a measure of spread. IQR, those are the two main ones that we study in Math 127, but range could fall on this list. These three statistics tell us how much spread there is in a data set. Okay? Measures of position, essentially everything else. Mean and median. All the quartiles, all the percentiles. Minimum, maximum. And for all purposes, this is basically what we study in this course. Okay, these are measures of position, these are measures of spread. Make sure we can classify our statistics so that if we multiply or add, subtract or divide, we'll know what to do with the statistics. All right, we flip the page. We'll go back to this neighborhood in Elkton. Example, one neighborhood in Elkton, lot sizes are listed in square feet. And hopefully you can see this on the screen, but this first house in row 1, 202 Friendship, square footage was 1918. Second one, square footage was 2,048, and so on. There were, I think, about 40 houses in this data set. Lot sizes in square feet. The mean is 15,746. Median's 11,282. We've got a minimum of 66,64 and a maximum of 64,904. A couple measures of spread given here. Standard deviation was 11,511 and IQR was 6796. Okay. Question A here, do you think the distribution was skewed or symmetric? If it was skewed, which way and why? Okay. The main clue I can use to answer this question is I could look at the mean and the median. Okay. Let me just remind myself what the numbers are here. The mean was 15,746. That is a lot bigger than the median of 11,282. That will clue me in terms of the shape. Okay. Definitely skewed. If the mean and median were the same, then we would guess that the data looked symmetric. But definitely skewed, and which way? Skewed right. Skewed right because that mean is a heck of a lot bigger than the median. There are probably some high outliers that are pulling the mean up and making it about 3,000 square feet larger than the median, right? If I had to guess, without seeing the data, I'll put a question mark here, but there are probably a few high outliers, houses in the neighborhood with bigger lots than is typical. Okay, that's part A. We'll move to B. Part B, if lot sizes were expressed in acres rather than square feet. Now, typically, we might think of a lot size in terms of acres. What would the new summary statistics be? There are 43,560 square feet to 1 acre. Okay, so think about your data. I need to take lot size, excuse me. We're doing lot size. I need to take lot size and convert it to acres. This first lot size is 11,761 square feet. How many acres is that? I would take each of these and divide them by 43,560. Okay, so let's write that down. This is a scale. What we would do is we would divide lot size, the existing in square feet, we would divide everything by 43,560. Once we did that, then lot size would be reported in acres, not square feet. All right, I did all this at home. I'll write down the summary statistics, and I guess we can, maybe I'll go to the sideboard and just make a list here. The new mean would be, I take the old mean, because I'm dividing all my data by 43,560, all of the statistics, everything, measures of center, measures of position, measures of spread, everything gets divided by the 43,560. So here's what would happen. New mean is 15,746 divided by 43,560. If you do that at home, I trust that you can, you get 0.361 acres. So the average lot size is a little bit more than 1/3 of an acre. Take every statistic, divide by 43,560. I'll just give you the answers. I won't break this out every time. Okay? So here we go. New median. Dividing it out, the new median is now 0.259. Again, that's in acres. Putting the units, making sure we emphasize that. The new minimum, if we divide it out, 0.153 acres. The new maximum, so the largest lot in this neighborhood is 1.49 acres. And we had those two measures of spread, standard deviation. We would divide the old standard deviation by the 43,560. New standard deviation, 0.264. That's in acres. And to wrap it up, that new IQR is 0.156 acres. Once you've got the first one, it's pretty easy. Just follow the pattern. Everything in that list gets divided. Okay, we just did a scale because we divided. All right, to wrap up this example, There's a part C, and what I want to do is just look at the two histograms. Notice the similarities and differences between the original data. This is the original data here. This was in square footage. Over on this side, this is the new data after we did the scale. The shape's exactly the same. It originally skewed right, as we learned up in part A. You can see we skewed right for sure. Long tail to the right. And after I transformed my data, the transformed data is also skewed right. Okay, so the shape is identical. Right, outliers are going to be the same, etc. The only thing we did is we changed the scale. Now I'll make one comment and then we'll move on. In the original data, my histogram goes from 0 up to about 70,000 square feet. Okay. After I divided everything by 43,560, I printed this graph so that the scales would fit nicely on this slide. But for the new data, this only goes from 0 up to 1.561. If I put these on the same scale, the shape would stay the same, but this would get condensed down to, I mean, literally about 1 millimeter here. Okay, because in terms of acres, our values only go from about 0 to 1.5. When I printed the graph, I wanted the scales to be the same, just to show you that the shape's identical. Would get totally smushed down. All right, I think we've got one last page to go here. Wrap up this lesson on shifting and scaling. Example, we sent Cecil students to Walmart a few semesters ago. What we did is we asked students to pick one food item and get the price. Okay. Histogram and summary statistics are listed below. So we had over 100 students go to Walmart. They picked whatever food item they wanted to, Hot Pockets, for example, or 12-pack of Coke. And the histogram has the prices. So down here is a little bit under $1, and almost everything was up to about, what, $6.50 maybe. And we had this one high outlier that was over $10. Skewed right again, definitely a high outlier here. Possibly a few here. We could do the outlier rule of thumb. All right, we'll flip the slide. I've got the summary statistics. 100 on the dot products. The average price was $2.70. Median was $2.58, and I won't read the rest of the summary statistics. But let's look at two scenarios and wrap up this lesson. Part A: if Walmart ran 50 cents off on every single food item, what would happen to each statistic? All right, 50 cents off means take every price and subtract off 50 cents. This is definitely a shift. This is a shift. This says let's subtract 0.50 from every food item, every price that we have. Okay? Give the new summary statistics. We still have, N is still 100, right? We still have 100 data values. The mean used to be 270. If I subtract 50 cents from every price, the new mean, subtract 50, this will go to $2.20. All right. What happens to standard deviation? This is a measure of spread. Okay, for that matter, let me put a box around them. The range is a measure of spread. Way down here, IQR is a measure of spread. Think of the data values on a number line. Now I'm subtracting 50 cents from every one of them. They used to be here. Now they're here. No change to the standard deviation, range, or IQR. So we'll just copy those straight down. 140, standard deviation. 1029 would be the new range, and $1.48 would be the new IQR. All right. Median, min, max, quartiles, these are all measures of position. 50 cents gets subtracted. Hopefully I can do this in my head without looking at my notes. 258 was the old median, goes down to 208. We'd subtract 50 cents. 69 cents was the old minimum, back off 50 cents. New minimum would be 19 cents. The 1098 for the maximum goes to 1048. The 181 for Q1 would go down to 131. And the 329 would go to $2.79. It's a shift. This is what would happen. All right, I think there's a part B. Maybe it's a scale. Sort of has to be, right, students? We didn't do one of those yet. Part B, if Walmart ran 10% off every food item, what would happen to each statistic? 10% off food items. What that means, if it's 10% off, you're paying 90%. You're paying 90%. So this is a scale, and everything gets multiplied. If the old mean was 270, then the new mean is 90% of 270. I'm subtracting 10% off. Everything gets multiplied by 0.9. Measures of center, measures of spread, all those measures of position by 0.9. So, I can't really do this one in my head. I wrote them down. We still have 100 data values. The new mean used to be 270. New mean is 2.43. Standard deviation will get multiplied by 0.9. New one is 1.26. New median, $2.32. New range, $9.26. New minimum, 0.62. New maximum, $9.88. Q1 changes to 1.63. Q3 changes to 2.96. And IQR changes 1.33. This whole row of data values is just 0.9 times the top row. It's a scale. Everything gets multiplied. All right, that wraps up this video for I. Thanks for watching, and we'll see you next time.